Okay, I'm going to take the opportunity here to introduce the dot product, which is in the future, at least for 285 students, and we're probably going to touch on it with 177 students, and just touch on it, kind of just about as much as we're going to touch on it here. The dot product of two vectors in Rn is written, okay, if this is the first vector, and well, I'll just say this is the first vector, this is the second vector. I want to do the dot product of this vector with this vector, and I write that. I write the first vector, I make a big dot for the dot product, and I write the second vector. And that's equal something very, very simple. This times this, first component times first component, added to second component times second component, added to third component times third component, added to fourth component times fourth component, added to the fifth component times the fifth component. Now in this case, that calculation is really straightforward, and I don't really need a parenthesis there, so I'll sloppily get rid of it, okay? Now we understand what I did. I multiplied these numbers, I multiplied these numbers, these numbers, these numbers, and these numbers, and I add the products. It kind of reminds you of multiplying a row by a column, but that's not exactly what's going on, but yeah, it sort of is. If you regard this as your row and this as your column, that's kind of exactly what you have. So we could define the dot product to be the product of the first vector expressed as a row multiplied by the second vector expressed as a column. Well, not hard to see that that's 0. You get -2 here, you get 2 here, that adds up to 0, and everything else, every other product has at least 1 0 in it. Okay? Now, that's kind of a big deal. Vectors are said to be orthogonal if their dot product is 0. Now that's just a generalization of perpendicularity, okay? And since perpendicular lines have negative reciprocal slopes, we could conclude very quickly, and if you want to think about it, it'd be a good idea, but you don't have to, that the dot product of two vectors in R2 is going to be 0 if they're perpendicular, and if they're perpendicular, the dot product is going to be 0. If they have negative reciprocal slopes, it comes out of just that consideration. So those vectors would be said to be orthogonal. Now orthogonality goes way beyond perpendicularity. So we use the bigger word orthogonal. But you can just think of it in Rn as vectors being perpendicular. Now what's in R3, it's clear what perpendicular means. And in higher dimensions, it extends in a pretty obvious way. Okay? Another thing that the dot product is good for, we define the magnitude of a vector to be the square root of the dot product of the vector with itself. Okay? And for vectors in R2 or R3, that just corresponds to the Pythagorean theorem. Okay, the magnitude of the vector is just its length. Dot product of a vector with itself is the length of a vector if the vector is in R2 or R3. Pythagorean theorem guarantees that. It's equivalent to the Pythagorean theorem. Okay, well that's denoted by like an absolute value of V, but it's an absolute value with an attitude, so we use two little bars on either side. We say absolute value of V then is V dot V, and that's the magnitude of V. This, as I said, is just an extension of the Pythagorean theorem. Now what does that have to do with anything that we're doing? Well, this vector is just this vector in the null space. And this vector is just the first row of the A matrix that we used, of which this is the basis of the null space. So I'm going to stick my neck out and say that if I've done all this right, and actually I'm starting to think that maybe I did when I corrected this here, that Any of these vectors, if I've done this right, should be orthogonal to each of these vectors. Okay? In other words, when I do the dot product of any row with either of these vectors, I should get 0, showing that the null space is orthogonal to the row space. So that's kind of a big deal. Either vector in the basis of the null space is orthogonal to any row of the A, and as far as that goes, to any row you get in reducing A using the valid row operations. So we say that the null space is orthogonal to the row space. And that's just using this simple dot product. Now, we haven't proven any of the properties of the dot product, so we're kind of using it prematurely. But this is a really kind of a big deal result, so I couldn't resist inserting it here.